Welcome back. Here is another interesting question. I find it very interesting. Let's start from this. By the way, my name is Sosale Mahana, and I am a teacher of mathematics who has taught for over 50 years, now retired, of course, and I'm using these lessons to help you revise your examinations based on what you learned in school. Right. When I did my A-level, they didn't give this. They just gave this and this. They didn't give this. Anyway, it's a big question, interesting question, and you're going to you get an insight into how forensic science works, how they determine. Remember, in some of those detective movies, you'll see, where were you between 6:45 and 7:20 p.m. on this particular day? An alibi. You need an alibi for the time of death. We are estimating a time of death using differential equations. It's pretty interesting. Let's understand this. Newton's law of cooling states the rate at which a hot body cools. See, if you keep a hot body in a room, it starts cooling. Initially, it cools very fast, but as time goes by, it slows down. Why? Because it's proportional to the excess of temperature of the body over that of its surroundings, assumed constant. Meaning, let's say you take a cup which is about 90 degrees Celsius, boiling water, very hot water, keep it in room about 20. To start with, the rate at which it cools is proportional to 90 minus 20, which is 70. After 10 minutes, let's say it has come down to 70 degrees, then it is between 70 and 20, 50. Then after 20 minutes, it will come down to about 40 degrees, it will be 40 minus 20, which is 20. So, the cooling depends upon, that means the rate of fall of temperature keeps on changing depending upon the difference. You understand that? Okay. So, the variables here are the temperature of the body and the time t in minutes. Because, fortunately for you, those variables have been identified for you here. I hope you can see what I'm writing there. Okay. So, if theta is the temperature of a hot body at time t, so the rate of cooling is d theta by dt is proportional to the excess of temperature of the body over that of the surroundings. The temperature of the body is theta, surroundings is assumed to be theta r, so it's proportional to that. Remember, theta is decreasing, so I'll say d theta by dt is minus k times theta minus theta r. Separate the variables. 1 over theta minus theta r d theta equal to minus k dt. Remember, theta r is a constant. So if I integrate it, I get ln theta minus theta r equal to minus kt plus ln a. So ln theta minus theta r minus ln a equals minus kt. I can rub this off now because I have used all that information. So therefore, ln theta minus theta r over a is minus kt. So theta minus theta r over a is e power minus kt. Theta minus theta r is a e power minus kt. That gives you this particular answer. So theta equal to theta r plus a e power minus kt. You're asked to show that. By the way, doesn't get it 10,000 marks. Newton's law will be given, whereas when I did my A level, they just said, using Newton's law of cooling, estimate. None of those things were given. We have to remember, even though we're doing maths, you might be doing maths, economics, geography, it doesn't matter. You have to know Newton's law of cooling. You have to know half-life period, radioactivity. All a part of maths are differential equations. So therefore, I'm going to rub this off because I'm going to use this space to answer each bit as we go on. So I'm assuming now the temperature is theta time t. You have been given a murder victim is discovered at 4:30 a.m. So you assume 4:30 a.m. is t equal to 0. The room temperature is 20 and the temperature of the dead body is 30 degrees Celsius. Okay. The police surgeon arrives at 5:10 a.m. 5:10 a.m. means T equal to 40. The room temperature is assumed to be constant, but the body has cooled to 27. I have been given two sets of conditions. I have two unknowns A and K. Remember, any unknown you bring, it's your job to solve. So therefore, I need to find what is A, I need to find what is K. So theta equal to, theta R is 20 plus A e power minus kt, t equal to 0, theta equal to 30. So 30 equal to 20 plus A e power 0, so A is 10. So theta equal to 20 plus 10 e power minus kt. I found the A. 5:10 a.m. is T is 40. T equal to 40, theta equal to 27. So 27 equal to 20 plus 10 e power minus 40k. So e power minus 40k equals 7 over 10, which is 0.7. So minus 40k equals ln 0.7. So k equal to minus 1 over 40 ln 0.7. The unknowns A and K were introduced by us. So our job to evaluate. Right, let me see how to evaluate that. ln 0.7, ln 0.7 equal to that divided by 40. I will ignore the minus sign. It is 0.00892. So therefore, I can put all these things back. I can rub this off. Except you must remember 4:30 is t equal to 0. T equal to 0, or let me write it here. T equal to 0 is 4:30 a.m. and theta equal to 20 plus 10 e to the power 0.00892 t. You see, I only have two unknowns. So we have now got a relation between body temperature and the time. The man was alive when his temperature was 37 degrees Celsius. So you assume theta to be 37. What do I get? 37 equal to 20 plus 10 e power minus 0.00892 t. So e power minus 0.00892 t equal to 37 minus 20 is 17. 17 divided by 10 is 1.7. So t equal to ln 1.7 divided by minus 0.00892. The answer for t will be negative. Can you guess why? Because we're going backwards in time to find out when the man was alive. Boom. So ln 1.7 is that divided by 0.00892. 59.48 or 59 minutes. 59.48. So approximately 59 minutes. Find to the nearest minute the time of death. So 4:30, 60 minutes is 3:30, 59 minutes is 3:31. So 3:31 a.m. Well, theoretically speaking, the man was sleeping. Maybe he was awake. 3:30, there, 3:31, he died. But doesn't happen that way because we do not know. They haven't yet found the investigate. The doctor doesn't know what are the circumstances. So comment on your estimate. Look, maybe the room temperature was not a constant. Maybe there was a big fire roaring, so it could have been about 32, and over the night the temperature has fallen off. The fire has died out. So by the time the surgeon came, might have cooled still further. You assumed it to be 20 degrees Celsius. So there is no guarantee that the room temperature, so the one comment you would make is, the room temperature may not be a constant. Second, circumstances of death. If one is scared, if you're scared, your body temperature goes down. So maybe the man was murdered. So we don't know. He was so scared. So his body temperature instead of 37 could have been 35. 2 degrees. Possible. Or maybe the man was agitated. They had an argument. They're having a fist fight. In which case your adrenaline flows, your temperature goes up. So you might have been 38 degrees Celsius. So the comment you're making is the room temperature may vary. Number two, the body temperature depends upon the circumstances of death. So that's why those are the comments you're going to make. Even though mathematically it's an estimate, it need not be correct. But then, how do you account for it? So generally, 3:30, so take about 15 minutes before and 15 minutes after. 3:15 and 3:45 a.m. So time of death would be between 3:15 a.m. and 3:45 a.m. So if you're one of the suspects, if I'm one of the suspects, the police inspector will come and ask me, where were you between 3:15 and 3:45 in the morning on Wednesday, the 13th of April 2022? I'm assuming the murder took place yesterday night. I don't know where I was. Maybe I was traveling on train. Maybe I was lying unconscious somewhere. I was sleeping at home all alone. Then I don't have an alibi because there is no one to prove that I was at home. Yeah? Anyway, one of those things. But pretty interesting question, isn't it? I don't know that I have time to do one more question in this. It's about 13 minutes. So, but the next question is a very big question. So I don't think I'll be able to do this. I will do it as a separate question. Very interesting question, another one. These are again, this, I had come across this, was an A-level question, similar one. Of course, the numbers might be different, the temperature and other things may be different. Way back early in the 1980s, in one of the A-level practice papers or textbooks, I had come across this question. Newton's law of cooling is the principle of physics, but it's applied to differential equations. You see, first I showed you about radioactive decay. There's also, I think, I don't know whether I did one on, not too sure. I might have done one on the number of fish in a pond, growth and decay. You can apply it to growth and decay and apply Newton's law of cooling. You can apply to mixtures and chemicals and solutions. In fact, there was one AEA question. These days it's called AQA, but way back in the 80s it was called AEA, where, they were talking of a reaction where 5 molecules of a particular chemical and 3 molecules of another chemical join together to make one molecule of a compound. Initially, they were X molecules of the first type and Y of the second type, and the rate at which it was made was proportional to the product of X and Y remaining at time t. That was a brilliant question. I can't remember the exact figures, otherwise I would have done it. No, 85, 2022. That's 37 years ago. I can't remember the question 37 years ago. And it was, I was not teaching AQA then, I was teaching Cambridge A level if I'm correct. And they had Excel. So I came across this question. I did a practice in my class. If you can go back to any of the AQA questions, they used to produce booklets, AQA. And it was in that a beautiful question. Very interesting, challenging. Anyway, so I will see you in the next lesson when I will do just one more question before we do the final lesson on differential equation and say goodbye to you people. Okay? So I will see you when you see me. Bye-bye. Hello. I want to take this opportunity to propose a vote of thanks. I would like to thank Vivid Innovations Private Limited and Commerce Forum for so generously giving up their studio and the facilities and the services of their technicians to record all these videos for free. I think that needs to be acknowledged and appreciated. Thank you very much. And my special thanks to Mr. Nitin Mahadevappa, Mr. Nishant Guruswamy, and Mr. Sadan Kumar DN for all their help and assistance in getting these videos ready, uploaded, and launched. Thank you very much.